This is my third video about gravitation, and it's about gravitational energy, which I know a lot of students find tricky. It takes a while to get your head around this. Gravitational energy. Now, how much GPE does a 1 kilogram mass have on the surface of the Earth? And before this, you might be thinking 0, but the answer is actually minus 63 million joules. A kilogram mass on the surface of the Earth has minus 63 million joules of gravitational potential energy. Why is it so much, and why is it negative? Well, in the first year when you did GPE and at GCSE, hopefully you recognize delta GPE equals mg delta h. And we can do this in a uniform field. Force times distance, mg times delta h. Now, on a planetary universal scale, you can't use this equation because g isn't constant. G varies with distance. You need another way of defining gravitational potential energy. Okay? Firstly, we say that an object has 0 potential energy, not on the surface of the Earth, but at infinity. Infinity is a very, very, very long way from everything. It's in deep space. It's on the edge of deep space. It's a theoretical place. It's a very, very, very long way from any mass. And we define a quantity you've not met before at A level called gravitational potential. What do we mean by gravitational potential? Now, a useful way of thinking about it is that the potential at a point in space is the potential energy that a 1 kilogram mass would have at that point. The actual proper definition is that the potential at a point in space is the work required to take a 1 kilogram mass from infinity to that point. That's what you'll read in a textbook. A few things about potential which are worth remembering. Remember, it's joules per kilogram. It's the potential energy of a kilogram, joules per kilogram. And like potential energy, it's negative. In these planetary universal fields, potential energy is a negative quantity. It is negative. Also remember, it's not the property of an object, it's the property of a point in space, the potential at a point in space. So V equals minus gm over r. I'll talk about where that equation comes from later. Gravitational potential, how much GPE 1 kilogram would have at a point. So m times v is gravitational potential energy. That would tell me the GPE of a mass m at a certain point. And then m delta v is the energy transferred when a mass m moves between 2 points with different potentials. If you moved away from the Earth, it's how much work you would have to do. If something moved towards the Earth, like an asteroid or whatever, it's how much kinetic energy it would gain as it moved towards the Earth, m delta v. Here's a sum that you can have a go at, a very typical kind of A-level question. Have a read, have a go at it. And the answer is, there you go. There's its kinetic energy, there's its GPE, mv, and its total energy is that. Notice that the total energy is negative. If the total energy wasn't negative, then the satellite would escape. And that leads us on to escape velocity. What do we mean by the escape velocity of a planet? The escape velocity of a planet or a moon or a large object, if you projected an object upwards from the surface of the Earth, how fast would it have to be traveling so as to escape the Earth's gravitational field? Ignoring air resistance, our energy equation, so kinetic energy goes to GPE, so half mv squared goes to mgm over r, rearranging that for v. Work it out for yourself. Worth remembering, the escape velocity of the Earth is about 11 kilometers per second. The escape velocity of the Earth. A useful idea in physics is potential wells. Imagine you are trapped inside a well on the surface of the Earth. You can't escape from the Earth. You can't go flying off like Superman and have adventures around the solar system and the universe. You're trapped in a well. To escape from this well, you would have to do a lot of work. You would have to climb out of the well. It does get easier and easier as you climb out because the well gets less steep. But you have to do an awful lot of work to climb out of the well to get to infinity. And if on your way out you let go, you'd be pulled back in again. You would lose potential energy and gain kinetic energy. Equipotentials. This is a diagram. The red hashed lines on this diagram are equipotentials. The grey lines are field lines, usually drawn as hashed lines. What is an equipotential? Well, any point on the same equipotential has the same potential. In this diagram here around the Earth, we talk about equipotential surfaces, and they are spherical. They're not actually circles, they're spheres. Notice how they get further apart as you move away from the Earth. As it gets easier to move away from the Earth, for the same energy transferred, you would travel a bigger distance. You can think of equipotentials as like contour lines on a map. On the last slide, I talked about potential wells, and these are the contour lines for my potential well. Here are the graphs of little g and v against r. Notice the differences between them. Notice that the little g graph is an inverse square law, whereas the v graph is just inverse. And notice that the v graph is negative. I draw the g graph as positive, but the v graph is negative. Now, some interesting things again about this graph which you need to know. The area under the g graph tells us something interesting, and the slope, the gradient of the v graph, tells us something interesting. And what it is, the area under the graph of g against r between a point and infinity tells us the potential at that point. And if you're a proper A-level mathematician, you should know that v is the integral of g dr. If you integrate the expression for g, you get the expression for v. And similarly, g equals dv dr. So the gradient of a graph of v against r at any point tells us the field strength at that point. G is dv dr at any point. Okay, our field strength is the potential gradient.